Good morning to all. So today I will be presenting my individual project for course 696, quantum computing. My project is entitled as quantum teleportation and Bell state implementation. So let's begin with the presentation. So just like in classical computation, we have bits 0 and 1. Similarly, in quantum computing, we have qubits, and these are single qubits, 0 vector and 1 vector. And similarly there can be multiple qubits also. And what are multiple qubits? They are just the tensor product of these single qubits. And so these 0 and 1, they are the standard basis vectors in 2 dimension, and their tensor product will give the standard basis vectors in 4 dimension, C4. So these are the vectors 0 0 0 1 1 0 and 1 1. Now this 2 qubit system, it can exist in superposition of these 4 states. Here is the example, this I vector, and these alpha, and each of the vector is associated with a coefficient, with a complex coefficient alpha 0 0, alpha 0 1, and a square of their and sum of their square should be equal to 1, because it will then satisfy the probability condition. And suppose if we want to measure this 0 0 vector, then we will measure this 0 0 vector with probability alpha 0 0 mod square here. And suppose if we want to measure the first qubit, if we do not want to measure this vector, if we want to measure the first qubit, so probability of measuring the first qubit as 0 is given by, 0 is coming only in these 2 situations, so it will be alpha 0 0 mod square plus alpha 0 1 mod square, and our post measurement state will be this xi prime, and this is nothing but just the normalization constant. So these are some of the computations or some of the maths associated with qubits and multiple qubit systems. Now entanglement. So there exist many 2 qubit systems. Their superposition is such that it cannot be factorized as product of the standard basis vectors. So these alpha, beta, gamma, delta does not exist for this equation holds true, for which this equation holds true. So these are entangled states. So for 2 qubit system, we have only 4 possible entangled states, and they are known as Bell states. So these are the 4 Bell states. And to achieve these Bell states, this is the circuit. So let's understand this circuit. We have we have 2 input x and y. We are applying a Hadamard gate on the first qubit, and after that we are applying a C0 gate, keeping first bit as our control bit. So this is one of the so I have shown one example here. If we give 0 0 as our input, and so this is how we will end up in getting this Bell state 1 by root 2 0 0 plus 1 1. And this is a table which describes how we can get all the 4 Bell states if we have these inputs. Now we have Greenberger-Horn-Zeilinger states, known as GHZ states. So these are entangled states involving at least 3 qubits, or it can involve more than 3 qubits. So here is a generalized equation for obtaining GHZ states. It is not completely generalized. Somewhat it is generalized. If we have m qubits, then we will end up in this kind of GHZ state. So simplest 3 qubit GHZ state would be this simple to understand. Then let's then comes quantum teleportation. Quantum teleportation is itself implementation of Bell states. So quantum teleportation is achieved using Bell states. So what it is a technique of sending a quantum information from one point in space to another point in space. Alice has a qubit which she wants to send to Bob, and she does not know the state of her qubit. And initially, Alice and Bob, they share a Bell state between them, and they share 1 qubit each of the Bell states. So this first qubit 0 and 1, it belongs to Alice, this first 2 bits, and this second bit it belongs to Bob. So initially we have this Bell state and this qubit xi vector which Alice wants to teleport. So we have, so if we multiply all these vectors, so we can see that these 2 bits, they belong to Alice. and the third bit, it belongs to Bob. So bit 1 and bit 2 belongs to Alice, and bit 3 belongs to Bob. We have to keep this in mind because we will see why. And then Alice applies a C naught gate, keeping her first bit as the control bit, and she ends up in getting this. Then she applies a Hadamard gate, and and after doing some taking some common and factorization, we will get this. So these first two qubits belongs to Alice, and this is the third bit which belongs to Bob. So we can see after doing this, Alice measures her state. If Alice does a measurement on her share of the qubit, then and if she ends up in getting 0, 0, then she is successful in teleporting her qubit to Bob, because Bob will end up in getting this qubit. Okay. And if she measures her qubit and if she gets 0, 1, then Bob has to apply a bit flip gate in order to end up in the qubit which Alice wanted to teleport to him. So here is a table which describes elaborately that what Bob should apply if, according to the result of the measure of Alice measurement. So we can have a look on this table. Now, here we see that quantum teleportation, it seems that we have not talked about distance between Alice and Bob. So it seems that it can transport information faster than the speed of light. Is it so? It is not actually true, because in order for teleportation to take place, Alice has to send at least 2 bits of classical information to Bob. Okay, via the medium of phone call or any way, she has to she has to give 2 bits of information to Bob. Then only Bob can recover. Then only Bob can get the state which Alice wanted to teleport to him. Now, it also seems that teleportation, a copy of the state is created. A copy of the qubit, which is to be teleported, is created. But it is actually not the case, because it will then violate the no cloning principle. Because as soon as Alice measures her qubit, she is destroying her qubit. So there is no question of creating a copy of the qubit. Now, another implementation of quantum computing of this Bell state and quantum teleportation is super dense coding. It is in some sense a reverse of quantum teleportation. So Alice want to send 2 bits of classical information by sending 1 qubit of quantum information. Let's see how it is achieved. So this is the circuit, and it is just this is just the Bell state generation circuit. And after the generation of Bell state, Alice does some unitary measurements. Okay, and this is the Bell state measurement which Bob does. So let's see Alice. So if Alice wants to send, so initially Alice and Bob, they have they share Bell state between them. And if Alice want to share send 0, 0, 0, 0 classical bits, then Alice has to do nothing. And if she wants to send 0, 1, then she has to apply an X gate on her qubit. And similarly, here is the table. So what Bob receives, Bob applies a C naught gate. And if he applies a C naught gate, keeping first qubit as the control bit, he end up in getting this. So after applying C naught gate, Bob measures the second bit. If he gets 0, then he comes to the conclusion that Alice must have sent either 0, 0 or 1, 1. And if he measures second qubit and if he gets 1, then he comes to the conclusion that that Alice must have sent either 0, 1 or 1, 0. Then Bob applies the Hadamard gate, and after applying Hadamard gate, he measures the first qubit. And if he measures the first qubit and it comes 0, then he comes to the conclusion that Alice must have sent either 0, 0 or 0, 1. So there are 2 situations. Here Bob does 2 measurements. After applying C naught gate, he measures the second qubit, and after applying Hadamard gate, he measures the first qubit. And what results he get, according to the result of his measurement, he comes to this conclusion. So let's see a table which very elaborately describes this. If Bob measures the second qubit and if it comes 0, then he concludes that Alice must have either sent 0, 0 or 1, 1. And if he measures his first qubit after applying the Hadamard gate and it comes 0, then he comes to the conclusion that Alice must have either sent 0, 0 or 0, 1. So in order to decode the information which Alice wanted to share to Bob, he has to take the intersection of these two sets, and the intersection of these two sets is actually the result, is actually is the result which Alice wanted to share to Bob. So similarly, we have these situations, and we can have a look on this table. So this is super dense coding. So another implementation of this Bell state and quantum teleportation is that quantum teleportation can be used to build quantum gates which are resistant to the effects of noise. And another implementation is that quantum teleportation is intimately connected with the properties of quantum error correcting codes. So I have not elaborately discussed here these two concepts because the lack of space, and also because of the lack of information. So let's conclude our presentation with some bullet points. So teleportation is itself an implementation of Bell states. Alice can teleport her quantum state to Bob by sending 2 bits of classical information, irrespective of the distance between them. And in teleportation, it is not possible to transmit information greater than the speed of light, because there must be a classical communication between Alice and Bob. And there is no violation of no cloning principle in quantum teleportation, as it seems. There is no violation, because after Alice measures her qubit, she destroys her qubit. Then comes super dense coding. Alice wants to send 2 bits of classical information by sending 1 qubit of quantum information, and she achieves her goal. She is successful in achieving her goal. We have seen very elaborately how she achieves her goal. We have seen the circuit, we have seen the table, we have seen the logic, and lastly, the other implementations of quantum teleportation are building quantum gates which are resistant to effects of noise, and also it is used in properties of quantum error correcting codes. So with this, I will conclude my presentation. Thank you.